Okay, let's get going. Today we're going to pick up some stuff from Tuesday that we did not finish, and also get into talking about choosing prior distributions. So let's get the fact that I work at Columbia. Stan is developed mostly at Columbia with the support of a lot of research grants. I try to use Stan outside of Columbia, and that creates the appearance of a conflict of interest. So if we go back to last time, we were thinking about working with a posterior distribution where we had a gamma prior over the expected value of the number of people who live in an apartment or a house. And then we might be planning to collect some data in observations where we go to different houses and apartments, find out how many people live there. So that is going to be a count. And it has some expectation. That expectation is what we want the posterior distribution of. And because we're dealing with count data, and so far we only know of one distribution that's defined on non-negative integers, that's the Poisson, we're going to use that. So we have a gamma distribution with shape parameters A and B, which can be obtained based on your prior mode and prior expectation of what mu is. You can solve two equations or two unknowns to get the shape A and the rate B. And then we have a Poisson PMF, the conditional distribution of the data given mu, which, as we talked about, can be written in a more simplified form, such as the one in blue here, when we're talking about the probability of observing n observations rather than merely one. And so we take our prior PDF and Poisson likelihood, then the posterior distribution of mu is going, given the data and what we believe is going into it, is going to be proportional to the product of the prior PMF and the likelihood, ignoring the denominator for now. I'm also going to ignore the constants in the prior, which is B over A divided by gamma A, and the constants in the likelihood, which is the product of 1 over the factorial for each of the data points. If I'd kept those terms in the numerator, then when I perform the integral over the numerator and divide by whatever that is in the denominator, the constants are going to cancel out anyway. So it doesn't matter if I get rid of them up front or leave them in, but it's less stuff to write and keep track of when I don't. And so by dropping those things, those terms that don't depend on mu, I'm left with what's known as the kernel of the posterior distribution. There was a question on Campus Wire. I may have mentioned kernel before actually defining it. The kernel of some distribution are the terms in the PDF that actually pertain to the random variable in question, in this case, mu. And everything that's left off is the constant or the normalizing constant. In this case, the normalizing constants may depend on B and A and whatever, but B and A are known, as well as the data are known. So that factorial term is known. So you can always separate for a distribution PMF the part that involves the random variable in question, that would be the kernel, and the part that does not involve the random variable in question, the normalizing constant, which merely ensures that the PDF integrates to 1 or the PMF sums to 1. So I'm just working with the kernel here, the terms that involve mu, throwing away the constants. And you can see that the contribution from the, well, I wrote it in the wrong colors. The part that comes from here which is now in blue from the prior, and the part that comes from here, which is now in red, is the part that comes from the likelihood, have similar terms. So in both cases, we have mu raised to some power, and then we have e raised to some power involving a scalar multiplied by mu. So we can combine those terms together to get the purple version of the posterior kernel. That's going to be mu raised to the power a minus 1 plus the sum of the y observations times e raised to the power quantity negative of b plus n times mu. And if we simplify by making substitutions a star and b star, where a star is equal to a plus the sum of the count observations on the outcome, and b star is equal to b plus the number of observations that we have in our data set, then we see that the posterior kernel can be written as mu to the a star minus 1 times e to the negative b star times mu, which is the same kernel as the kernel of the gamma prior that we started with. Therefore, we know that the denominator has to have the normalizing constant of a gamma PDF, but evaluated at b star and a star rather than evaluated at a and b. So we see, just similar to the case where we had a beta prior and a binomial likelihood for the Ebola example, this is another special case where if we have a gamma prior and a Poisson likelihood, we say those are naturally conjugate with each other. Conditioning on Poisson distributed data updates my prior, but it stays to the posterior, but it stays in the gamma family. So I start with a gamma prior with shape A and B. I end up with a gamma posterior with shape A star and rate B star. So it kept it in the same family, but it updated the parameters to that gamma distribution. That won't always be the case, that the posterior is in the same family as the prior. Indeed, in general, it isn't. But there are a handful of special cases where that is true, and it's easy to come up with examples where you can see the process of updating your beliefs as you get more data in. And that's always going to, in the case where it's naturally conjugate, involve the same family between posterior and prior, just increasing the value of the parameters so you get a more precise estimate of the random variable you're interested in this case, mu. Questions about that? So I showed this on Tuesday, but just to go through it again, we had, we wrote this kernel function in Stan, and then we numerically integrated to find the denominator. Just divide that numerator by the denominator, and we get the black line here, which you can barely see because it's obscured by the blue line and the green line. The green line is the analytical form of the posterior distribution based on plotting the gamma PDF with shape A star and rate B star. Then we also have a kernel density approximation to this posterior PDF that was obtained when we got 10,000 draws from this posterior distribution by drawing from the prior predictive distribution and seeing if the sum of that exactly matched the sum of the data points that we had. And then finally, we can contrast all that with a plot of the curve in red of the prior that we started with, gamma PDF with shape A and rate B. So the black, the green, and the blue lines are all equivalent to each other. There's some approximation error with the blue one, but you can see it's basically talking about the same thing. But all three stand in contrast to the prior distribution, and our posterior distribution, after observing the data that I put up last time, has been shifted to the left and gotten more concentrated. Now, each one of these curves has an area of 1 underneath them because they're valid PDFs. And you can sort of intuitively see that they have the same area. But the way in which they're distributed, the way in which they're reallocated over our parameter space when we condition on data changes depending on what the values of the data are, which is why Krushke describes the process of Bayesian inference as reallocation of credibility across possibilities. Possibilities are all positive real numbers in this case, but we've reallocated from something that's characterized by the red curve to something that's characterized by one of the other curves when we condition on observed data. Questions about that? Okay. So based on this information we have here, what do you believe about future data point? Like if you were to go to a new apartment that you haven't been to yet and find out how many people live there, how would you describe your beliefs about that?
Well, when you just did the mean of this new posterior, so maybe a tad over 2 people.
Would you expect to see a tad over 2 people in an apartment?
Well, I mean, I guess 2. What's a rate?
I've never been to an apartment that had a tad over 2 people.
Right.
I've been to an apartment that had like a tad over 200 people, but
okay, so then you would expect 2, but if you sample 10 households, you would expect on average a little over 2.
yeah, on average, let's just say 1. You just went to 1 more new one. How would you describe your beliefs about the number of people that live there? 2. And so how did you get that?
It's about where the posterior peaks.
So approximately the posterior mode. Okay, that's one way of looking at it. Anybody else? The posterior mode is not going to be exactly 2 either. So it's not an integer. Usually apartments, houses, integer number of people. Somebody else. Well, how did you form your beliefs about how many people there would be in an apartment before you saw the data? What distribution did we assume was for the data conditional on the unknown parameter? On the previous slide. False signs. Right. So that is convenient because it's actually a random or distribution over integer random variables. Okay, so how could we use the Poisson to get a prediction for a future apartment house that we go to see how many people live there?
I mean, could we simulate draws from our posterior for the for mu, and then take the mean of, or plug those into the Poisson to take the mean of what occurs?
Yeah, we could. We could do all that. Or we could do all that and not take the mean. Because the answer to a question, what do you believe, is never a number. It's always a distribution, a function. Now, the expectation of what you believe, that's a number. The mode of what you believe, that's a number. The median of what you believe, that's a number. But the answer to what you believe had better be a distribution that integrates to 1 or sums to 1 in the case of a discrete random variable. And so this is another case where we can work out analytically what that distribution is, utilizing what I like to refer to as the Bayesian hokey pokey. If you want a PDF for a future y value, conditional on the y values you've already observed, what that is the integral from 0 to infinity of the joint distribution between the future y value and mu integrated over mu. So the joint distribution of future data and mu marginalizing out mu. So you introduce mu and you integrate it out. So the joint distribution between future y and mu is the posterior distribution of mu given the past data multiplied by the conditional PMF for future data given mu. That can be written with gammas or a gamma distribution evaluated y star, a star, and b star, and a Poisson PMF for the conditional distribution of future data given mu. Pull out the constants, combine the red and blue terms inside the integral. We get another thing that is in the form of a gamma integral, which is something that computers can accurately evaluate. And what we're left with is this expression involving, these terms here, which is one among about 12 different ways to write the probability mass function for the so-called negative binomial distribution, which is also defined on a sample space of non-negative integers. And so it too would be appropriate for counts. Negative binomial distribution has expectation in this case of a star over b star, but unlike the Poisson distribution whose variance was equal to the expectation, in this case the variance of a negative binomial is equal to the expectation plus a star divided by b star squared. Both a star and b star are positive, so the variance of a negative binomial distribution is going to be greater than its expectation. The the negative binomial distribution is going to have more variance than a Poisson distribution, even if they both have the same expectation. And the reason why we have extra variance relative to Poisson distribution is the Poisson variance of the Poisson distribution given mu is mu. So if you knew what mu was exactly, then the variance of your predictions about a future apartment or residence would be exactly Poisson, and it would have expectation of mu and a variance of mu. But you don't know what mu is exactly. You still have a considerable amount of uncertainty about what mu is. And so when forming your predictions about how many people live in an apartment or a house that you haven't been to yet, you have to propagate your uncertainty about mu into your predictions. So we have a conditional distribution for number of people who live in a house or apartment given mu, but we're uncertain about what mu is. And so we have to take these draws from the posterior distribution, put them into the Poisson PMF, and then we do that a whole bunch of times. What we're left with is a marginal distribution, a marginal predictive distribution for the number of people that live in a future apartment or house that has taken into account already our uncertainty about what mu is. And that is a really fundamental point of Bayesian inference, that you always have to be keeping track of your uncertainty and propagating it through these functions of random variables that may be of interest to you. Does everybody understand that? You don't know mu, so you need a distribution for mu to plug into the Poisson PMF, and that distribution of mu is the posterior distribution of mu that you got given the data that you've already observed. So it forms a very coherent way of doing inference, and if you're just leaving off uncertainty here and there, then you lose that coherence. So you can do this in R using the R pause function, and R functions that generate random numbers from some distribution are usually going to start with a lowercase r and then have some suffix on them. So remember, post is 10,000 draws from the posterior distribution of mu I got from drawing from the prior, drawing realizations for what I predicted the data to be before I saw it, keeping the draw from the mu if it exactly matched the sum of the observed data points, etc. So I have 10,000 draws from the posterior distribution that I pass to the expectation of the Poisson random number generator and get back 10,000 predictions for what a number of people living in a future apartment or residence would be. I can make a histogram or a bar plot or whatever of those because it's discrete. And I'm left with a posterior predictive distribution for the number of people in the next apartment or residence that I go to that looks like this in terms of proportions of draws that fall on each of the non-negative integers. And so that's the answer to the question, what are your beliefs about a number of people living in a future apartment? Okay. So what's wrong with this? Yeah.
I'm confused at least by why everything outside of the region 1 to 3 has a decent probability of occurring. Is the mean and the posterior strongly suggested between a 1 to 3?
Right. So the posterior distribution represented here of mu, the average, the expected number of people, is, a little bit over 2. But the predictive distribution is defined over a different space, the non-negative integers. And so, yeah, we have these here. And, maybe you're saying, well, this looks a little bit farther to the left than what you may have thought based on the posterior distribution. But it's got a relatively long right tail to it, where there's, at least a noticeable probability of there being 9 people in a house. And so if you take these proportions representing the probability mass function of your predictive distribution, use those to weight all the non-negative integers, you're going to get an expectation. And under a negative binomial distribution, that's going to be the same expectation as your posterior expectation for mu. But, it is definitely concentrated on 1s and 2s, but with a somewhat extreme tail. So anyway, what's wrong with these predictions? Yes.
Is it that's just one combination of
It's 10,000.
but that's still just one combination of 10,000.
Yeah. I mean, I could do a billion and you could call it one combination of a billion. It's still going to look about like this in proportional terms. All right, anybody here try to rent an apartment in New York? Anyone? Anyone? Yeah. How many, in terms of rough guess of the proportion of the number of apartments in New York, were vacant when you tried to rent it? Right, 15%. Not many. And yet we predict 12% of the apartments are going to have 0 people in them. So 0 is possible. 12% being 0 in Manhattan, not possible. So this is a poor distribution for the number of people living in apartments in Manhattan because it overrepresents empty apartments. It might be appropriate for someplace like Detroit where nobody wants to live anymore. but you can look at your predictive distribution and see evidence, oh, maybe something in my generative model was wrong. Could be the prior, could be the conditional distribution of the data given the unknown, could be your software didn't work right, could be your code has a bug in it, could be a lot of things, but you can get a hint that something went wrong or is wrong by looking at the predictive distribution for observed outcomes. And you can do that, you should have done it already by simulating from the prior predictive distribution and notice that you were predicting like 20% being vacant apartments. And so you should have figured it out right then. But if you don't, you can get it from the posterior predictive distribution, also saying like, this is not going to be capturing an important feature of, you know, residence, occupancy, whatever, in New York, at least, or most anywhere else that people actually want to live. Questions about that? Yeah?
I have a question. So basically, there are tens of the posterior values of the distribution, right? And so it's for each of the draw, I draw a random realization of the possible. Why is there only be one of that, not like any given draw from the posterior?
Right. So we do generate one draw from the prior predictive distribution, which is Poisson, for each of our posterior draws of mu. And I had 10,000 posterior draws of mu. And for each one of those, I get one draw from the predictive distribution. So altogether, I had 10,000 draws from both the posterior distribution and the posterior predictive distribution for people to do. And that's important. What you don't want to do, but a lot of people do, is just take the posterior distribution, collapse it to its mean or its median or its mode, even worse, and then take one draw from a Poisson. And then they try to make a bar plot out of one draw. And that does not adequately reflect your uncertainty in how many people you would predict would be in a new apartment or house that you haven't been to yet. Because by collapsing an entire posterior distribution to its median or its mode or its mean, you throw away all that uncertainty that you still had left in your posterior distribution. So you have to take the whole posterior distribution and put it in to the predictive distribution. And by whole, I mean with like thousands of draws. So you adequately capture all that in proportion to its posterior density. Other questions about the posterior predictive distribution? Mark.
How do we have a binomial distribution for non-negative?
How do we have a Poisson? Well, so it's technically Poisson. So this goes out to infinity. We just didn't actually get any realizations that were bigger than 9. So there's no upper bound here. But almost all of the posterior mass is a single-digit number, which does make sense for apartments and houses. Just too much on 0 and probably not enough on like 3 and 4. Other questions? Okay, so we've seen 4 or 3 actually, but there's 4, there's actually more, but we've seen so far 3 out of 4 ways of executing Bayes' rule. First, you can draw from the prior predictive distribution, which is to say draw a realization from the prior, stick that realization from the prior into the conditional distribution where you draw a prediction for the data. And if the predictions exactly match the data that you have, keep your realization from the prior as a realization from the posterior distribution. And that works really well with outcomes that are small integers, and it's extraordinarily inefficient or maybe impossible when the outcome is continuous. But it's very good at conveying the intuition as to what Bayes' rule is doing when we condition on observed data. We have our beliefs about the parameter, which is represented in its marginal prior distribution. We compose that with a conditional distribution for the outcomes given the unknown parameters. That gives us a joint bivariate distribution between the unknown parameters and the predicted data before we see it. And then from that joint distribution, we're going to keep the parts of it that are consistent with the data that we observe over n observations. So we have this whole joint distribution before we see the data of realizations from the prior and predictions from the conditional distribution of the data given the unknown parameters. And we're going to selectively keep part of that distribution. We're only going to keep the draws that come from the part of that distribution that are consistent with the data that we observe. That is conditioning on observed data, and those draws are valid draws from the posterior distribution, but we can't do that, get this exact matching really except in cases with a binomial. Another thing that we've done 2 or 3 times now is to write the numerator of Bayes' rule either with or without the constants, preferably without because it's easier and it's equivalent to do the same thing, but numerically integrate the numerator of Bayes' rule in order to get the denominator of Bayes' rule using the integrate function in R, which is effectively using little trapezoids. And so then we can get the number that is in the denominator of Bayes' rule, divide that function that we've defined for the numerator by whatever that number is that is spit out by the integrate function. And now we have a posterior PDF for the unknown parameters that integrates to 1, and thus we could interpret it in terms of probability theory. And, you know, that's fine, and it follows pretty directly from Bayes' rule, but it's pretty much only within the realm of possibility when we have a single unknown parameter. If we had 2 parameters, then we'd have to do a double integral in order to get the denominator of Bayes' rule, and trying to do with numerical integration in 2 dimensions is already basically not very accurate for the most part. Maybe in some cases you could do it okay, but you can't do little trapezoids anymore. Now you have to do little prisms because you're integrating over 2 dimensions. Anyway, beyond a couple parameters, this is going to be hopeless to do numerically, even though it works pretty solidly as long as you only have 1 parameter. But most of the models that we're interested in the social sciences are going to have more than 1 parameter. So we need a more general approach. The third that we've seen come up with the posterior PDF analytically by exploiting the fact that prior is naturally conjugate with a likelihood. And so the posterior PDF is in the same family as the prior PDF, but with updated parameters that go into that distribution, like A star and B star, and just figure out what A star and B star is. That is fine when it's possible to make those calculations analytically, when the prior is conjugate, naturally conjugate with the likelihood. And this is good because it makes the fact that the Bayesian updating of your beliefs very explicit. And it's apparent from these A star and B star formulas that it doesn't matter if you got like 1 data point at a time and you updated your beliefs n times, or you got n data points all at once and you updated your beliefs once, or you got like half the data this week and the other half the data next week and you updated your beliefs twice. In the end, you're going to end up in the same place with A star and B star, as if it didn't matter how the data came to you. You're going to end up with the same beliefs. And you can use your posterior, in the case where it's naturally conjugate, you can use your posterior PDF after the first batch of data as your prior PDF for when you're going to condition on your second batch of data. And the results that you get at the end are going to be a posterior PDF that is the same as if you just started with your prior beliefs and you got all the data in one batch. And that's one of the fundamental characteristics of Bayesian learning, Bayesian updating. But again, there's not that many situations in which we can get these integrals even semi-analytical solution, even including, you know, special functions like the gamma function or the beta function, things like that. There's, you know, maybe about 20 examples that could be done this way, and we've done 2 or 3 so far. But again, it's mostly limited to the case where you have one parameter. Sometimes it works with 2 if you assume one of the parameters is known, but you never really know the parameter. It never works when you have like 10 parameters or anything like that. So we're going to need a fourth and a more general way to execute Bayes' rule, which is to use Markov chain Monte Carlo, specifically the algorithm that is implemented in Stan, to sample from these posterior distributions. And the good thing about Markov chain Monte Carlo is it doesn't require you to have the denominator of Bayes' rule, just the numerator. But you are going to have to tell Stan what posterior distribution you want to draw from. And the way you communicate that to Stan is by saying, here's the numerator that defines the posterior distribution that I want you, Stan, to draw from. Now, you know, go ahead and do it. Give me back 4,000 or whatever draws from this posterior distribution, and I'll work with the draws rather than work with the normalized PDF. And that is actually more convenient in a lot of ways, and you can do anything you want with the draws. And as long as you have enough of them, it gives you way more accuracy than you really need anyway. So we've done the first 3 a couple of times. We'll start in with the 4th next week and just continue using Stan in, you know, more and more intensively as the weeks and months progress on. So, you know, with Bayesians, it's all about seeking the posterior distribution. And because we're ultimately interested in making decisions or conclusions by getting expectations of some function G. So G could be like utility or, you know, accuracy in estimating a parameter, something like that. And we want the expectation of that function with respect to the posterior distribution, the conditional distribution of the parameters given the data that we've actually observed. And we know from the definition of expectation that this is just going to take the function that we're interested in, weight it by the probability that theta is in a little interval around d theta, and integrating over all the parameters that are in our model. Let's say there's k of them. In general, that can be more than 1. So that gives us the expectation of this substantive function that we're interested in, but our substantive function depends on unknown things about the world like parameters theta. But we want to weight it using a posterior PDF for the conditional distribution of these unknowns given the data that we do know. So conditional distribution of unknowns given known data. And that's really the essence of, you know, Bayesian decision theory, and the reason why we do Bayesian estimation in the first place is to make good, sound decisions based on the limited information in the data that we have, to update our beliefs about the parameters when we have to make a decision or a conclusion. Now, there's a lot of people out there that don't really appreciate how fundamental the distinction between the goals of Bayesian inference and the purported goals of frequentist inference, the way people like Fisher and Neyman stated them, even though Fisher and Neyman disagreed with each other a lot and basically hated each other, and one ran the other out of England and whatever. It was a long time ago. But anyway, they had issues, but they're sort of the, you know, forefathers of frequentist inference, who are, particularly with Neyman, ultimately interested in a different expectation, the expectation of some H function that depends on the data. And so that is the integral of the H function, weighted by the PDF or PMF of the data conditional on the parameters, and integrated over the possible values that the data could take. So in the case of Bayesian inference, we're integrating over the parameter space. In the case of frequentist inference, we're taking expectations by integrating over the sample space, omega. So we're doing these integrals with respect to what the data could be, conditional on the parameters. And so H could be some point estimator or interval estimator of the parameters theta, and it's being weighted by the likelihood function, the conditional distribution of the data given theta, except it's not really the likelihood function because we're actually considering it to be a function of y for given theta here. But anyway, so we see, okay, they're both taking expectations of some function that is of interest to them, but the functions of interest are different. The expectation by definition of probability in the case of continuous random variables involves integrals. And to a lot of people, they're saying, well, you know, both of these involve integrals. I don't really know how to do integrals anyway. So both of these integrals are like the same as far as I'm concerned, which is mathematically ridiculous. Because in one case, you're integrating over theta, and in the other case, you're integrating over y. In one case, you're weighting with the conditional distribution of the unknowns parameters theta given the known data. In the other case, you're weighting with the conditional distribution of the data given the parameters theta. And the reason why frequentists do this, even though they're never actually given theta, is they want to come up with H functions, estimators of theta, that have good or at least known properties. And when they do that, they're like, okay, this estimator has like decent properties. Everybody use it. Because if it were used over, you know, tons of data sets, different realizations of y, if we get a distribution of the estimator that we can live with. But as a result of it, frequentists have put themselves in a situation where they can't say anything probabilistically about any particular set of estimates. So for your data set and the estimate that you get from it, can't really say anything about it. It's not even a random variable. Over everybody's data set that is using this H function as its estimator, then we can say, okay, that has a distribution and maybe we can live with it. And in particular, that comes up in the case of confidence intervals, where H is a function that returns 1 if and only if the true parameter theta is between some lower bound and some upper bound. So if that is our H function and we take the expectation of it, we want it to come out to be 0.95 if it's a 95% confidence interval, or come out to 0.9 if we want a 90% confidence interval. But for both of these, in order to evaluate that function, we would have to be given theta. But given theta, we could construct lower bounds and upper bounds such that this interval would capture the true parameter theta 95% of the time if we applied it repeatedly to thousands of data sets. And okay, so that may establish that this estimator is sort of good overall, but it's still going to be wrong, or it's not going to capture the true parameter 5%, 10% of the time, depending on what the confidence interval is. And we have no way of knowing for any particular estimate that we obtain, like 0.42 or whatever, whether, or, you know, between 0.42 and 0.76, for any particular data set, any particular realization of that confidence interval, we can't say whether it contains the true parameter or not. We can't even say there's a 95% probability that this confidence interval between 0.42 and 0.76 contains the true parameter, because this realization of the confidence interval is not a random variable. The whole 0.95 thing, the whole expectation thing, refers to the distribution of the point estimates as a whole across many, many, many data sets. And so frequentist approach to probability is really all about the forest and not about the trees at all. So we could say something about the distribution of an estimator, can't say anything probabilistically about any particular estimate obtained from that estimator. But if everybody is using this estimator, then, you know, collectively we can live with that. But I would say that's not really what most researchers sign up for. They care about their particular research, their particular tree. Something is writing on the conclusions that they get from a particular study, and they want that to be, you know, as good, as sound as possible, given the data that they have. They didn't collect, you know, spend 2 years of their life going to different countries and whatnot, collecting data in order for someone to care, well, that's just a tree, we only care about the forest. It's your tree. So there's a lot writing on particular realizations, you know, from data sets, conditioning on them and updating your beliefs about parameters, and making maybe big decisions as a result of that. You know, in the poker problem on the homework, there was millions of dollars writing on the decision made in that one particular hand. And it was for a situation that like basically never comes up. So it's sort of ridiculous to say, well, you know, over all poker hands as a whole, you know, there would be like, you know, this property or whatever, the person would win, you know, some proportion of the time. But when you're in a particular poker hand, you know, it's just the information that you have on that particular hand, and you need to make the best decision possible in that context. And that really points you more toward the Bayesian approach to inference, rather than, you know, Neyman Pearson or, you know, anything from Fisher or any of these old, now dead frequentist guys. Questions about that? So the reading from Lancaster today got into a little bit about the different perspectives on different approaches to inference, but really, like, in one of the things that he says in the reading is that when people have taken a couple of classes that have only looked at things from a frequentist perspective, it's hard for them to understand like what the Bayesian thing is, or like why it would be different from what they already know, or how something that they use so much and they see other people being used so much doesn't really match up with the perspective on probability that everybody seems to be taking, where probability is degree of belief that something that you don't know is true, rather than the proportion of time something happens as you do a random experiment over and over and over and over again. But, you know, that's the way it is still. So Stan, it's just a language for manipulating probability distributions. And as such, you can do frequentist things with Stan. Stan isn't going to make it any worse than it already was. So we'll do a frequentist example here using the Stan language, again, declaring a function. This is based on the 1.4 example and the Lancaster reading, where we want to estimate or get the distribution of an estimator for the parameter in an auto-regressive model, which is one of the basic models for time series. When you're saying, you know, what my model for what happens today is proportional to what it was yesterday. And there's some coefficient on the outcome from yesterday that governs, you know, the conditional expectation for what the outcome is today. And I want to estimate that coefficient using, for example, like least squares. But before you can do frequentist inference, somebody has to establish the properties of the proposed estimator. And that's really what frequentist approach to statistics is all about. And so, you know, a lot of people have been in office hours and whatnot saying like they're finding this, you know, Bayesian material like difficult to do and things like that. But if it makes you feel any better, you're even worse at frequentist inference, like real frequentist inference. You just know how to get R or Stata or whatever to give you the estimates. Actually generating and understanding the distribution of estimator is something that you would find really difficult if you were asked to, you know, actually do it. But we need to know the properties of these estimators before we can just announce on Twitter that everyone's supposed to use it now or whatever. Anyway, so this is an evaluation of a least squares estimator for the coefficient in an AR1 process. So this is going to return a vector of point estimates. It's going to take in an int s, how many simulations I want to do, t, the number of time periods of data that I'm going to use to estimate the coefficient. It's going to take mu, which is my unconditional expectation for the outcome, rho, which is the true value of the autoregressive coefficient, and sigma, which is the standard deviation of the errors in my time series process. And so you'll notice right away that when you define one of these functions and you're going to evaluate an estimator from a frequentist perspective, you take in the parameters as arguments to your function. Everything that we're doing on this is conditional on the parameters because we want a PDF, a distribution for an estimator given the parameters, even though in reality we're not going to have the parameters, but we want to know it's okay to use the estimator to estimate the parameters that we're taking as given, but we don't really have. But we could have them in a simulation, and perhaps that's good enough. Anyway, inside the body of the function, I'm declaring a vector of size s to hold my point estimates of rho, the autoregressive coefficient. I create a constant alpha, which is the intercept in an AR1 model, mu times 1 minus rho, and define t minus 1 as a constant I'll need. Check that my parameters are valid before I drop into a for loop from 1 to capital S. So inside my for loop, I'm going to repeatedly simulate data under an AR1 process, and then I'm going to apply the least squares estimator to the data I've simulated, conditional on the parameters that govern the process. So I'm going to allocate a vector of size t for y, the outcome, set the first one equal to 0, or actually it should be mu, but mu is 0 in the example I do, and then loop from 2 up to whatever is the maximum value, the number of time periods that I'm considering here, and set yt equal to alpha plus rho times whatever y was in the previous period, plus an error that's randomly drawn from a normal distribution with expectation 0 and standard deviation sigma. That happens and gives me the outcome at time t. And then after I've done all that, I'm going to drop into another piece inside the curly braces where I take out the first t minus 1 of those and call that y lag. And then I take out the last t minus 1 of those and call that y temp. And then I can execute the OLS estimator as this expression here. So in the Stan language, dot star means element-wise multiplication. That's different from in R where you can use just star for element-wise multiplication of two vectors, and you have to use something else, which we'll talk about some other time, if you want to do like actual matrix multiplication of vectors or whatever. In Stan, it's different. So dot star refers to element-wise multiplication of vectors, and plain star refers to vector multiplication of vectors, but we're not to vector multiplication of vectors yet. So anyway, we want the element-wise product of the forward version of y and the lag version of y, all that summed up, divided by the sum of the squares of the lags. That is the OLS estimator for the coefficient on the lag of y term in the AR1 process. So when that loop completes, I can return the point estimates that I've obtained by repeatedly simulating data under a known AR1 process, because I know the parameters, because I passed them into the function, execute my OLS estimator, and now I'm in a position to evaluate how good that estimator is given known parameters. So questions about what this function does, which is using Stan syntax, but to evaluate a frequentist point estimator, the OLS estimator of a regression coefficient in an AR1 model.
Can you tell me why it's unconditional mean? What's it, why do you why
Yes. So mu is the unconditional mean of an AR1 process. So if I didn't condition on what happened yesterday, what would be the expectation of y? The conditional mean is given by this right here, alpha plus rho times yesterday.
So it's conditional on what happened yesterday. It's
Right.
conditional.
Yeah.
If there's no time, it's unconditional.
Right. So with the first observation that you have in your data set, you can't condition on what was before the first observation. So that's just unconditionally mu, which in this case is 0. But for all the ones forward, you can condition on yesterday. And so you get a conditional expectation. Okay, so we can expose that to our R session using rstan expose stan functions. Call it, we want 10,000 simulations, 51 time periods. Rho is 0.9. We get back very quickly a collection of point estimates that we can plot the density of. And so this is a probability distribution, a PDF of an estimator, of a point estimator, of a frequentist point estimator. And this is really what the essence of frequentism is all about, establishing that the properties of this estimate are good across 10,000 or whatever seems like a big number of simulated data sets. And if so, then we can announce on Twitter that everyone should use it on their particular data set. And we know that like the tens or millions of people on Twitter, that's going to collectively give us this distribution, at least when rho is 0.9, but the basic characteristics of this hold when rho is any other number. And so we can see for this estimator, well, the mode of the point estimates is to the right of the true value, which is 0.9. The mean, the expectation, because it has a long tail going to the left, is to the left of the true value at 0.9. The median of this distribution looks like it would be pretty close to 0.9. But how are we going to actually get the median unless we have 10,000 different data sets to apply this to and then take the median of those? If we're only, each individual person is just applying this estimator once, you just get like one random draw from the distribution whose PDF is the black curve there. But if you didn't actually know what rho was, how would you know or have any basis to say whether your estimate was too high or too low or any real description of a particular estimate other than it comes from an estimator that has this distribution? Now, there's, I guess, some sense in which, okay, we've like evaluated the property of this estimator across many simulated data sets and its properties are good. So everyone go ahead and use it. In this case, the properties of it aren't that great. It's a biased estimator, which is to say the expectation of the estimator is not equal to, indeed it's less than in this case, the thing that you're estimating. It's got a lot of variance to it. So its properties are not all that great, but they're known. And so, sometimes the devil you know is better than the devil you don't know, or Bayes is the devil, or something like that. But this is really what frequentism is about. And then this estimator gets programmed into Stata, and 10,000 people use it. And if 10,000 of people are using it when the true row that no one knows is 0.9, then they're going to get a collection. Collectively, they're going to get estimates that have this shape. And we know that. So that's what it is. Important points on the Lancaster reading. So it talks about this distinction between statistics and econometrics, which I really think boils down to people who don't have a generative model and are just sort of saying like, here's the mean of the data or something like that, versus people who are trying to specify a generative model for some process in the social sciences that they're interested in. Also emphasizes that you choosing your prior is not really a fundamentally different exercise than you choosing the distribution that you're going to use for the likelihood. Talks a lot about using simulated data or predictive data, and that can actually be better for understanding what's going on and the pitfalls and things like that than, you know, what I call wild data or data that are collected from the world. So you always want to make sure that your Stan programs and whatnot are working on simulated data before you try them on wild data. Because Bayesian inference is conditional on the n observations that you have and no other observations. So there's no like, what if we were to do this like 10,000 times and get different observations every time? There's no real important distinction from the Bayesian perspective between the sample and the population. So frequentist inference, that's a fundamental distinction. You're using a relatively small random sample from a population in order to make inferences about the parameters that govern in the population. And, you know, in reality, nobody has a simple random sample from a population, but they apply these estimators anyway. But anyway, the thought is the random experiment is each time we get a different sample from this population, apply the estimator, do that over and over again, and we can talk about the probability distribution of estimators. But from a Bayesian approach, you don't have to have a distinction between population and sample. So you're just conditioning on the observations you have in your data set. Any observations that may have been in the population but not in your data set are not relevant to your inferences because you're not conditioning on them because you don't have them. And so the posterior distributions that you get out are representing of what your beliefs are about those parameters, conditional on the n observations that you actually have. So you'll see people refer to the data as a sample when they're doing a Bayesian estimator, but that's not really necessary. It certainly doesn't need to be simple random sample or cluster random sampling or anything like that. It can just be the data that you've collected and you're making a description, an updated description of your beliefs about the parameters that govern the generation of those n data points that you actually have, and extrapolating it to other data points that you haven't gotten yet. Well, you're not conditioning on those. You could get the posterior predictive distribution of those. We did that at the start of class today. But in terms of what you're conditioning on, it's just the data that you have without any extra assumption that this is a random sample from some population or anything like that. So last 12 minutes, I want to talk about principles by which you can choose prior distributions by, which is an important aspect of Bayesian inference. But these principles can also be used to choose what likelihood distributions to use. And I would say principles are as follows, and we'll go into each of these briefly. Don't use improper priors. They're not real priors. You could just simply use subjective priors that are designed to reflect what you believe or whatever your audience believes, and then you get the posterior distribution updated. McElreath and his hero Janes and a number of other people use the principle of entropy maximization to choose prior distributions. That's a little bit sometimes related to this idea that prior distributions should convey the same amount of information no matter how you parameterize things. So whether you use, you know, probability or log odds, like your prior should contain the same information no matter how you parameterize that thing. So that's one principle that you can use. There's another sort of pseudo principle of choosing objective or maybe uninformative priors, but that turns out to not actually be that objective. And another one, more recent, some people who work on Stan have introduced this idea of penalized complexity priors. And we'll cover that more when we get into hierarchical models after spring break. So we'll run through these first 5 in the last time that we have here today. So improper priors are ones whose PDF does not integrate to 1. So that's why I say it's not a real prior. Now, if it integrated to any constant, we could just divide by that constant, and now it integrates to 1, and we're fine again. So improper priors are the ones, the integral of the so-called PDF for an improper prior distribution, instead of that definite integral being some number that we can work out, the integral actually does not converge. So there is no definite integral that we can divide by to make the thing integrate to 1. And so these don't really represent a valid collection of uncertainty about your beliefs about these parameters. And you can't draw from these prior distributions because they're not really distributions. And one of the problems that you can run into is if you use the improper prior, then you might, even when you condition on the data, have an improper posterior distribution whose integral diverges rather than integrates to 1. And then you have something that's completely useless for doing Bayesian inference or taking the expectation of a utility function or anything like that. So in some situations, it's possible to use an improper prior condition on data and still get a proper posterior distribution, but you have to establish that on a case-by-case basis. If you instead you use proper priors, ones that do integrate to 1, those are always going to yield proper posterior distributions. So you're safe, and you don't have to establish on a case-by-case basis that your posterior distribution is legitimate. But even in the cases where improper prior still yields proper posterior distribution, you can't do things like Bayes factors, which we'll talk about in a couple weeks. And these can also be like very computationally problematic as well. So pretty much just don't use them, although you'll see other people doing so. Subjective priors. This is, I think, where it's been reflective of what we've done so far, and also the main approach taken in the Lancaster book that we read from today, which is just choose the priors that reflect your beliefs about the parameters as of now, or whoever you're trying to convince, your audience, like do it for them. And then, update those by conditioning on the data. This is also sometimes referred to as elicitation of priors, because you could go ask an expert what he or she believes about theta or mu or whatever. So there's this idea of you like climb to the top of some mountain and like ask an old guy, what is the prior mode of a beta distribution for the Ebola cure or whatever. And they like tell you some number, and then you walk down the mountain, collect the data, and then, update the posterior distribution. Now you'll find when you do this that the experts are not all cracked up as they think they are. They often do have like a lot of experience with the data and whatnot, but they know so little about probability that they're not really a whole lot of help when you ask them like, what's the prior median for this gamma distribution? And they're like, what's a median? So, for what it's worth. There has been recently some people who have a website called the Metalog distributions, who I think have made it much easier to specify subjective priors. And so what we've done so far is, with the Ebola example and the apartments example or whatever, is say like, what's your prior mean? What's your prior median? What's your prior expectation? And then we solve like 2 equations and 2 unknowns in order to get the parameters we need to use to plug in for the prior. And that's not that difficult, but a lot of people are like, math is hard or whatever. And so these people have come up with distributions called quantile parameterized distributions where you just choose your parameter space and then you specify some quantiles like the median, the 25th percentile, the 75th percentile, maybe a couple others. Are there lower bounds? Are there upper bounds? And if you specify that information, we can construct you a distribution that has those properties. Now, I'm running out of time, so I'm not going to be able to explain that in great detail today. We'll utilize these more as we go along. But let's just say you're like, okay, I need a prior distribution over a sample space between, or parameter space between 0 and 10. I have a median of 4.8, 25th percentile of pi, 75th percentile of 6.2. What would be a distribution that is consistent with that? We can construct that distribution, and there's its CDF. And quantiles of it, 25th, median, 75th, all exactly match up with what I said. So if you can, say what these quantiles are, or climb a mountain and then, talk to the old guy at the top of the mountain for what these are, then we have a family of distributions that is flexible enough to capture that information exactly. And you can use that to reflect you or the old guy at the top of the mountain's expert subjective beliefs about this parameter before you go to condition on the data. So that makes it real convenient. Don't have to solve two equations for two unknowns. They've already been solved for you. Entropy maximization. So another older principle of choosing a prior distribution is, well, choose the PDF for the unknown parameter conditional on like whatever information you have to maximize the expectation of the negative logarithm of that PDF. Subject to the constraints, PDF has to integrate to 1, and one or more constraints that the expectation of some function g is known. So if you specify these m values as to what the expectation of the g function should be, then those restrictions imply what form f has to take. So why might we want to do this? In the discrete case, so with like dice, the uniform distribution achieves the upper bound of entropy. And so we can interpret the entropy of a distribution as how close it is to a uniform distribution subject to the constraints that we put on it in terms of the expectation of these g functions. And this process can be used to choose both families for priors and for likelihoods. So what are these distributions that maximize entropy? If your parameter space is a closed set, then maximizing entropy is going to be the uniform distribution, or the uniform distribution is going to maximize that entropy. So standard uniform distribution is just going to have PDF that is equal to 1 for every value of theta on that unit interval parameter space. If you specify an expectation and a variance, or a standard deviation or whatever, and the parameter space who you're interested in putting a prior over is all real numbers, the normal distribution maximizes entropy. It is closest to a uniform distribution among all distributions that are proper, that have an expectation that is what you said, and a variance that is what you say. And you might say, well, the normal distribution doesn't look all that uniform. It looks like a bell curve. Well, it's the closest you can get to uniform for expectation this, variance that. So you're pinning down the expectation and the variance, and then saying, well, what gets me closest to a uniform? That's going to be a normal if your sample parameter space is all real numbers. What if your parameter space is just the positive real numbers? Maximum entropy distribution in that case is exponential for a given expectation. So if the expectation is like 2.4, then the closest you can get to uniform when the parameter space is all positive real numbers is an exponential with a distribution with an expectation of 2.4, or a rate of the reciprocal of 2.4. Same thing. Now you might say, well, it's kind of hard for me to think about expectation of a distribution like the exponential that's positively skewed. But you can utilize the fact the median of an exponential distribution is equal to mu times the logarithm of 2. So if the median is easier for you to think about, and I think for a lot of people it is, just think about the median, divide by the log of 2, and now you have the expectation that you need to use in order to maximize entropy in the case where the parameter is positive. Binomial and Poisson are both entropy maximizing for some conditions on the sample spaces where they're defined. So those are good choices for the likelihood when that applies. You can look on Wikipedia for a bunch more distributions that are maximum entropy in one case or another. But these are often going to have sort of weird constraints associated with them, but you can find them out. Finally, invariance to reparameterization. So the so-called Jeffreys prior for is going to be proportional to the square root of the Fisher information. Same Fisher who wanted to kill Jeffreys, but whatever. And that is the expectation of this second derivative of the log likelihood function. And so that has a formula or whatever. So if you can work those out. But one of the real adherents to this, guy named Jaynes, argued that the Jeffreys prior really only makes sense for a scale parameter. Yeah, like 10 more seconds. Really only makes sense for a scale parameter. So gamma distribution has a scale parameter, normal distribution has a scale parameter sigma, etc. In which case it is proportional to the reciprocal of that parameter. However, the Jeffreys prior in this case is improper, but this might be like the one case where it might be okay for you to improper prior. But anyway, the Jeffreys prior on a scale parameter is not non-informative. It conveys the information that the scale of the random variable doesn't have any substantive information. So if we're talking about income or whatever, it doesn't matter whether we measure income in dollars or euros or whatever. Those units contain no substantive information about the data generating process. And the Jeffreys prior is the only one that basically is invariant to changing the units. Okay, so apparently somebody else is going to be here. So we need to clear out. I will post the second homework tonight. It'll be due next week before class to give you more chance to practice probability with